In this lecture, I will talk about structure criteria for mixed mode loading. So our title in this lecture is structure criterion for mixed mode loading. Mixed mode loading. There are various structure criteria for mixed mode loading, but we will consider one of these criteria, commonly used one or simpler one somewhat, that is named as maximum circumferential stress criteria. So I will be considering maximum circumferential stress criterion. This accounts for or considers the maximum stress on a given theta line. What's the maximum stress on that line? And it was developed at Lehigh University by Fazıl Erdoğan and George C. And we will see how this is developed. We will first consider a crack under mixed mode loading. Suppose that this is a crack. A crack tip, crack plane, and that is the radial coordinate r at the crack tip. I'm going to consider stress elements, and this is the angle theta. Polar coordinates are measured with respect to the crack tip, and consider the stresses acting on this stress element or polar stress elements at the crack tip. We can show the stresses here. That's a plane problem, plane stress or strain. For two-dimensional stresses can be shown on the stress element. This is an enlarged diagram. And that is our element. And what are the components? And you know how to place polar components on this stress element. It's the radial stress, circumferential stress, and shear stresses with positive directions according to the positive sign convention of staticity. We can show stresses acting on at that particular point. And these are sigma r, sigma theta, and sigma r theta. These are the points of stress. And this particular criteria depends on maximum circumferential stress. And therefore, we will be looking into the variation of the circumferential stress. But what are the stresses and how can I find these stresses? We are not going to use the full field stresses. Here, we'll be working with asymptotic forms, asymptotic stress, asymptotic stresses as R goes to 0. We know how to derive these, or we know their forms as R goes to 0. And you know how to write them in the Cartesian coordinate system. Say that is the Cartesian coordinate system, where the corrective and asymptotic forms are known at the Cartesian coordinate system, and find them in the polar coordinate system. What are the stresses in the polar coordinate system? That is the question. And we know that we can do this by stress transformation. This is rotated to an angle of theta. If stresses in the xy coordinate system are known, you can find the stresses in the polar coordinate system from the elasticity or advanced strength of materials. We know how to apply a transformation formula. That's a sigma prime. Sigma prime is a transpose sigma times A, where A is the transformation matrix. But we will not go into the details of these computations. I'm going to directly write down the results for sigma theta, sigma r theta. All of them can be found. But of particular interest here is sigma theta. So let me write an asymptotic form for circumferential stress. This can be found by transformation, and the results of final result is sigma theta equals K1 over square root of 2 pi r times 3 over 4 cosine theta over 2 plus 1 over 4 cosine 3 theta over 2. There's the mode 1 contribution plus K2 over square root of 2 pi r times minus 3 over 4 sine theta over 2 minus 3 over 4 sine 3 theta over 2. This is the asymptotic form for sigma theta. In a similar way, you can find the expressions for sigma r theta, sigma r. It's possible to derive all these stress components. And now, what is maximum circumferential stress criterion? And what are the underlying assumptions of these criteria? The first one, the first assumption states that crack initiation or fracture occurs at a theta angle for which sigma theta is maximum, hence the name maximum circumferential stress criterion. Therefore, we can indicate this as assumption 1. And this states that crack extension, which means fracture, initiates from its tip along the radial direction theta equals theta critical or theta c. on which sigma theta is maximum, or on which sigma theta becomes maximum. This is the first assumption. This criterion. And we can find the angle for which sigma theta becomes maximum by differentiating this. That is, you'll find, we intend to find the angle for which sigma theta becomes maximum. Therefore, consider for a given r, consider r as a parameter and try to find its derivative or equate the derivative to 0 to find the angle for which sigma theta goes to the maximum. And for that optimum point to be a maximum, the second derivative, d2 sigma theta 2 d theta 2. This has to be less than 0. That's the second condition. Now we can apply this, differentiate sigma theta here with respect to theta. We are going to differentiate it with respect to theta. Write the derivative, the sigma theta, d theta equals k1 over square root of 2 pi r. I'm differentiating the terms minus 1 over 2, 3 over 4, sine theta over 2, minus 3 over 2 times 1 over 4, sine 3 theta over 2. First one, differentiate the second one with respect to theta, k2 over square root of 2 pi r, minus 1 over 2, 3 over 4, cosine theta over 2, minus 3 over 2, 3 over 4, cosine 3 theta over 2, and this derivative is 0. Although it looks somewhat lengthier, but we can simplify it because factor out 1 over square root of 2 pi r and multiply both sides by 8, eliminate minus sign, and then you will find the necessary criterion as k1 times sine theta over 2 plus sine 3 theta over 2 plus the second term k2 times cosine theta over 2 plus, there's an extra 3 here, 3 times cosine 3 theta over 2, and this is 0. That neat result, which is going to give you the direction for crack propagation. This is our first result. I can use this to determine the angle theta critical. Calculate theta critical using this result. Now this is for the angle or direction, and we need to have a criterion for magnitude or loading, magnitude of loading. This was for direction. And that is related to assumption 2 in this Criterion by Erdogan and C. It states that at the point of fracture, maximum circumferential stress on theta critical plane is equivalent to maximum circumferential stress observed in mode 1 fracture, mode 1 failure. That is assumption 2. If we write it, it states that fracture initiates when maximum sigma theta has the same value as the maximum sigma theta computed for mode 1 fracture of the same material, of course. Second hypothesis of this criterion, which means that we have to substitute theta critical in this equation. Replace theta by theta critical in this equation, and you get K1 over square root of 2 pi r times 3 over 4 cosine theta critical over 2 plus 1 over 4 cosine 3 theta critical over 2 plus K2 over square root of 2 pi r times minus 3 over 4 sine theta critical over 2 minus 3 over 4 sine 3 theta critical over 2. This should be equivalent to maximum stress, maximum circumferential stress at the point of fracture for mode 1 loading, which is K2 over square root of 2 pi r. We can simplify this. These are cancelled out. Multiply both sides by 4. Cancel those out and multiply both sides by 4. I'll get the result for the second hypothesis. This problem, which becomes 3 times cosine theta critical over 2 plus cosine 3 theta critical over 2 K1 plus minus 3 sine theta critical over 2 minus 3 times sine 3 theta critical over 2 K2 equals 4KC. You see that these are cancelled out. when you multiply by 4, you get 3 here, 1 here, 3 here, minus 3 at the other end. Now, this is the second condition, and that's going to give you the loading associated with this failure criterion. Basically, there are two equations, two main equations, in other words, one, I can find case theta c to this, and 2. Calculate sigma, p, etc. parameters associated with loading. Any questions or comments on this result? I'm going to give an example for the application of this procedure. This is a hypothesis, but it is experimentally verified criterion. It agrees somewhat to a degree with experimental results, so it's in agreement with experimental results. Therefore, of course, there's a level of accuracy, however, it can be used to predict the onset of fracture for mixed mode problems. Now, this is valid for mixed mode problems as well as for pure mode 2 problems. And the first example I'll be talking about, say that example. This is related to pure mode 2 loading. But still, you have to implement this. You cannot, or we do not use mode 1 criteria for pure mode 2 loading. Geometry here involves a crack in infinite plane. Suppose that this is infinite plane. And there's a crack in infinite plane. There's the crack. Length of this is 2a. It's under remote shear. Therefore, this is mode 2. Remote shear type of loading. Flight stress is tau. And I can show the polar system at the crab tip. What are tau and theta? Tau critical and theta critical when fracture occurs because of this crack. Test problem statements. What are the values of these at the point of fracture? I can implement this first of all, what is K1 here? What's K1 for this problem? Yes, Jam gave the answer, that's 0. We know that this there is no mode 1 loading, therefore K1 is 0. And K2 is known. We have talked about these, or you considered such a geometry in the homework. K2 is tau times square root of pi a for this crack mode 2. Stress intensity factor is known. K1 and K2, they are known. Apply condition 1 first. What is the condition 1? If we go back, this is the condition 1. But K1 is 0. Therefore, K2 times the expression is 0. You can factor out K2, which means that cosine theta critical over 2 plus 3 times cosine 3 theta critical over 2 equals 0. That is the result for condition 1. Cosine, let me write it as theta, cosine theta over 2 plus 3 times cosine 3 theta over 2 equals 0. We have to solve this and find the roots in minus pi plus pi in this region. How can you solve this equation? Which math package are you going to use this to solve this? Probably MATLAB, is that right? I have solved it by Maple. With any math package, you'll be able to find the roots or apply a numerical method yourself. Newton-Raphson or any other suitable method can be used. There are 2 roots in this interval. One of them is minus 1.231 radius. And the second root is 1 over 1.331 radius. And which of the roots is to be selected here? Which one? And how can I find the actual root? This is related to the sign of the second derivative. If you recall, we have mentioned that d2 sigma theta, the theta 2 has to be negative for the particular root for it to give the maximum point. And if you evaluate second derivative, d2 sigma theta, dt2, the theta 2, k1 is 0, and the second derivative is k2. This is always positive over square root of 2 pi r, which is always positive. And if you evaluate the second derivative, you will find t over 16 sine theta over 2 plus 27 over 16 sine 3 theta over 2. Find the sign of this. Substitute theta 1, for example. Theta equals theta 1. The 2 sigma theta, the theta 2. This turns out to be negative. And for theta equals theta 2, 2 sigma theta, the theta 2 that's positive. Which of these is the actual root? Which one?
Theta 1.
Yes, that's right. Theta 1 is our solution, or the root. It gives crack direction. Crack extends along the direction minus 1.231 degrees, and we can now summarize this result.
Hocam neden negatif olması gerekiyor?
And that is the condition for a maximum point. It's from calculus, if you recall, the conditions for a function to be maximum point, f prime, let's say that a function of x at a certain point, if it's maximum, these conditions should be satisfied, and if it is a minimum point, f prime of x is 0, and so you review this from calculus, these conditions.
Aynen hocam.
And this is therefore found. Theta should be theta 1, and that is minus 1.231 radians. Or at a sharp angle, somewhat sharp angle of minus 70.5 degrees. If you show this crack broad path, if this is the crack under mixed mode loading, initial angle, we have found the initial angle, it will deviate from this straight line and it will extend in this direction. This is theta 1. And because of antisymmetry of mode 1 loadings, at the other side, actually it will extend to this direction. Crack under mixed mode loading will change direction and it will start its propagation or fracture process in these directions. This is theta 1. Now, theta 1 is known, but this is therefore critical angle, theta critical. And in the problem statement, we also ask theta critical, tau critical. What is the critical stress that causes this kind of crack propagation procedure? Critical stress, second assumption, and this, or the second equation. I'm going to go back to the second equation. We have derived this. Second one. K1 is 0, therefore we will consider this. Minus 3 sine theta critical over 2. Here, the first term. Minus 3 sine 3 theta critical over 2. Second term equals 4kc. And there's K2. Write down this result. We are going to use this second equation, which is minus 3 sine theta critical over 2 minus 3 sine 3 theta critical over 2 times K2, which is tau critical times square root of pi a. And this is 4kc. You can find, therefore, tau critical by applying this result. However, I have used certain numerical values. For example, I have taken Kc as 30 megapascals square root of meters, megapascal square root of meters. And I have used 10 millimeters for crack length. Theta critical is known. Calculate tau critical numerically. And that's going to give you, for example, 146.6 megapascals. This is the level of stress. And when you apply this stress, there is going to be a change in crack path, initial crack path, or this was a crack under shear loading, pure shear loading. And according to this criteria, when you apply this stress, the crack realigns itself and change direction, deviates from the center line. The crack is trying to become, the crack plane is trying to become normal to the direction of principal stress, actually. This occurs in crack problems. If you apply loading and as the crack grows, eventually crack plane will be perpendicular to the direction of principal stress. And it will try to become a purely mode 1 problem if it propagates. But we have here calculated the angle. What is the initial angle for crack propagation? There's hypotheses, answers in this problem. And what is the force or stress required to fracture the specimen, and which contains a crack? Again, this criterion tries to answer this question as well. There is a question whether we can use this in pure mode 1. No, you should not use this in pure mode 1 because you have to use the simpler form in pure mode 1 problems. This is not for pure mode 1. This is simplified for pure mode 1. And I have already given the simplified form for the pure mode 1 problem. What is the criterion for pure mode 1 problem?
Hocam, mode 1 at failure is equals to Kc.
Yes. In mode 1, theta critical is always 0. There is no need to find theta critical in mode 1 problems. It is always 0. We do not find it. And the second one reduces to K1 equals Kc. Therefore, this is the criterion for mode 1. K1 equals Kc, but the problem is more complicated. In mixed mode, we have to find both theta critical and loading. Crack always propagates on its own plane in mode 1 problems. You're welcome. And the crack is always propagating on the plane of symmetry in the mode 1 problem. Other questions about this? Zot? If you don't have any questions, I'm going to first stop the recording.